Welcome to lecture 38. In this lecture, I will talk about the cosmological redshift. Recall that in lecture 30, we discussed gravitational redshift in the Schwarzschild geometry. In this lecture, we revisit the same effect in an expanding FLRW universe. What we will find is that the scale factor and the redshift factor are related. Cosmologists use this relation to convert distances into redshift and vice versa, so it's an important relation to know about. To get started, recall that the energy of a photon, E, is given by Einstein's relation h bar omega, where omega is the frequency of the photon. In GR units and notation, we can write that E is minus the 4-vector product of the form momentum of the photon, p mu, and u mu. Here p mu is the form momentum, and u mu is the 4 velocity of the observer. This combination here is a contraction of two 4 vectors, and as such is a GR invariant quantity. Just to check, for a static observer, we have that its 4 velocity is just given as a time like 1, and there's no spatial velocity, so that the u mu with the lowercase index is just given as g00 and 0 in the velocity direction. So for a FLRW metric, we have g00 is minus 1. So if we plug this in, we find that this combination minus p mu u mu is nothing else but the 0 component of the form momentum, which is E, and g00, which is minus 1. So we find that this combination is just E, which is the starting point of where we had equation 38.1. Of course, 38.1 generalizes to more complicated situations. Now, for a photon, the form momentum can also be written as the derivative of the 4 coordinate x mu and an affine parameter lambda, which is the equivalent of the proper time for a massive particle, except that photons don't have a mass, so they don't have a proper time. So for a static observer in FLRW, we then have, this should be dx0 by d lambda, and that's the same as dt by d lambda. What we want to have is a relation between this energy and the scale factor A in FLRW. And we can use different relations for this. And the following will use the geodesic equation for photons to get this relation. Recall that the geodesic equation is a differential equation for the coordinate x mu and includes the Christoffel symbols gamma, mu, alpha, beta, which are properties of the metric that we want to evaluate this in. In the following, we want to specify to an FLRW metric and to photons that are traveling radially. So that means that their angular differences are 0. So they're just radially outward pointing. For this case, calculating the Christoffel symbols numerically or symbolically using a manipulation program for the FLRW metric, we find that this equation for the time-like direction becomes the equation 38.6. So you can see the Christoffel symbols over here, and we have specified to the case where the omega is equal to 0. In addition, we have that photons travel at the speed of light, so their line element squared is just 0. We can write this out again for radially outward traveling photons. We have that 0 is equal to minus dt squared plus the GRR, the radial component of the metric, which for FLRW is given as a squared over 1 minus kappa r squared. So we can use this relation to rewrite dr in terms of dt. And if we do so, we can rewrite this equation here in terms of dt only. The equation we get is listed in equation 38.8. That's the geodesic equation for radially traveling photons. We can solve this equation as follows. So we denote A dot is nothing else but dA by dt. And we can rewrite that as dA by d lambda times d lambda by dt. If we denote the derivatives with respect to lambda as primes, then we have that a dot is a prime over t prime. So plugging this into the equation up here, we get t double prime plus a prime over a times t prime is equal to 0. If we furthermore use the substitution t prime is y, this equation here becomes y prime is minus a prime over a y, which we can solve via direct integration. We find that y is a constant over a. Plugging this back into this equation, we can solve for dt, and we find that dt by d lambda is a constant over a. So now that we have the solution, we find that for a radially moving photon, its energy, which is given as dt by d lambda, is a constant over the scale factor a, which is the relation we've been trying to prove earlier. So since the photon's energy is proportional to its frequency, E is h bar omega, if we have two observers at times t1 and t2, they will measure frequencies omega 1 and omega 2 that are related by the ratio of the energies, which gives that the frequency ratio omega 1 over 2 is exactly equal to the scale factor ratio A2 over A1, where A2 and A1 correspond to the scale factors at time 2 and time 1. Because the scale factors will generally be different, this means that the frequencies will be different as well. And this means that photon frequencies appear redshifted in an FLRW metric. And the idea we want to behind this is that in an FLRW universe, the universe is expanding. So the expansion sort of has the same effect as a Doppler redshift that we have been investigating earlier. But of course, it's different because in this case, nothing needs to be moving. The objects can be in place. It's just a general relativistic effect that leads to a redshift in the frequencies. It is particularly useful to take one of these observers to be us today. So we take, for instance, T2 is equal to T0, where T0 is today's time. We can then introduce what's known as the cosmological redshift factor Z, which is omega minus omega naught divided by omega, where omega is the frequency of the originally emitted photon and omega 0 is the photon frequency that we observe today. Clearly, because of the relation that we had before, this is equal to, there must be something wrong here. So this there should be a typo over here. So this should be equal to A naught over A minus 1. And in terms of Z, this means that we get that A over A naught is equal to 1 over 1 plus Z. If there's no redshift, so if the photon is emitted today, then clearly there's no redshift. We have Z is 0, and Z is 0 just means that the scale factor A of t is equal to A of naught. Conversely, the bigger the redshift factor Z, the smaller A of t will be, and that means that we are looking at bigger differences in terms of time. Now, if you recall that there is a Taylor expansion of the scale factor that we did in lecture 36, the Taylor expansion up to linear order term involved this difference or ratio of the derivative of the scale factor with respect to the scale factor itself, which is known as the Hubble constant. If we now relate this to the relation in the redshift factor, 1 over 1 plus z, we have the following relation here. Now, since we know that we are expanding around t is t naught, which also implies z is 0, we know that z is small for this expansion, so we can expand for small z as well. And we find that t0 minus t times h naught is equal to z. Differently, the Hubble constant h naught is given by the redshift factor divided by the difference between t naught and the time of the emission of the photon, 4 small values of the redshift factor. So for small redshifts, the Hubble constant and Z are linearly related, which is a relation that is used quite a bit in cosmology. And this concludes the present lecture.